Hello everyone, welcome back to this continuation on our lecture series in Biophysics for health science majors. This topic will be getting into the senses of hearing and vision and the physics behind those two when it comes to sound and light. Both sound and light have to do with a concept called waves and wave types based off of how they propagate through certain media or certain materials. Waves are periodic oscillations that act as carriers for energy. The main two types differ by whether a physical medium is needed or not needed in order for the wave to propagate, to move forward in a particular direction. There are mechanical waves which require a physical medium to travel through. They can be longitudinal or transverse, and this includes sound waves and oscillations seen in strings and slinkies. Non-mechanical waves are those that do not require a physical medium in order to propagate through space. They are always transverse, and examples include electromagnetic waves, like anything that is light, for example, X-rays, radio waves, visible light, anything in the electromagnetic spectrum, as well as gravitational waves. Wave types by affected medium. Well, we have longitudinal waves, which are those where as a wave propagates along an axis, the medium is distorted parallel to the direction of propagation. This involves refraction, rare refraction, which is expansion, and compression. Sound waves act in this manner, as well as P-type earthquake waves. If we go to the bottom right corner, that would be an example of a longitudinal wave. As the wave is propagating to the right, so is the displacement of the medium it is traveling through, where certain parts are being pushed together and certain parts are being compressed further apart, parallel to the motion of wave propagation. There are also transverse waves, which as a wave propagates along an axis, the medium is distorted perpendicular to the direction of propagation. Examples include ripples in water, light waves as well, gravity waves, and S-type seismic waves. So the top red example, where the wave is propagating to the right, the medium that it is traveling through is being distorted up and down, or perpendicular to that motion of wave propagation. Some basic parameters and properties that are discussed when we look at waves. One is the frequency, which is the number of oscillations that wave goes through per second. The units are inverse seconds. Oscillations per second, which are also called hertz. There's also the period, which is the time required for one full oscillation to occur, and the units are in seconds. The wavelength, which is the physical distance from one point in the wave to the next point that is in the same height and point of propagation, same phase. This is typically in units of meters. So if we look at between two crests of a wave, two crests or two valleys, that distance would be one wavelength of that light. Some other properties we have is our maximum magnitude or our drop in magnitude. That is the height of the wave crest or wave valley between some baseline axis. We have our velocity of propagation, our linear velocity. And a correlation between frequency and time is that they're inverses of each other. If we know what frequency is, just take 1 over that to get the period. If we know what the period is, take the inverse of that to get frequency. Wave interference can be constructive and destructive. Let's look at, for example, two waves that are traveling in opposite directions. We have one wave traveling to the right, and we have another wave traveling to the left. And after a certain amount of time, wave 2 is now on the left, and wave 1 is now on the right. Well, what we see here is that as waves travel through each other, they haven't destroyed each other, and they pass right through each other. However, something interesting happens for the parts where they overlap. Let's say we're at the point where those waves are overlapping, where we essentially have the amplitude of one wave overlapping the negative amplitude of another wave. While that's happening, what would actually be observed is just the areas that are not overlapping, whereas the parts where there is positive and negative out-of-phase overlap, that would be destructive interference, where we would actually not see anything in the medium that it is traveling through. Now let's take the situation where both waves are now in the same phase, where the negative areas are overlapping, the positive amplitudes are overlapping. What this causes when both waves are overlapping in that manner is for the observed effect to be greater than either wave separately. Essentially, the overlap where everything is in phase with one another would be constructive interference, which gives us an observed amplitude that's greater than the individual waves separate. Sound waves are an example of waves. They exist as mechanical waves and specifically longitudinal mechanical waves. These can also be called pressure waves because of how they compress air as they travel through them. They can travel at 340 meters per second through air and 1500 meters per second through water and various biological tissues. Just like the waves that we talked about, they do have a wavelength and amplitude, crests and troughs. They do have, as they travel, they are going to compress the medium that they are in, and there will be points of lower compression or expansion, really, which are areas of rarefaction. The concept of beats is actually the cumulative periodic fluctuations heard in the intensity of sound as two waves of similar frequencies interfere with one another. For example, we have a series of one wave overlapping a second wave, the first being the top overlapping the second, and what we see here in green is the combination of interferences between constructive interference, where the amplitudes are larger than the individual waves, and destructive interference, where the amplitudes are much smaller than each individual wave. That is where beat arise, from the interference of different waves of similar frequency. Some characteristics of sound waves include loudness, pitch, and quality, where the last one can also be called timbre. When it comes to loudness, it distinguishes between loud and feeble sound. It mainly depends upon the amplitude of sound. Other factors are the area of the vibrating body and the distance of the listener from the source of sound. We can have high amplitude sound waves, which have loud sound, or low amplitude sound waves, which have low or feeble sound. Pitch, that distinguishes between shriller and flatter sounds. It mainly depends on the frequency of sound. Higher frequency or shorter wavelength is a shriller sound. Low frequency or a longer wavelength is a flatter sound. So, thus far, loudness is correlated to the amplitude of a wave, pitch is correlated to the frequency. Quality and timbre. This distinguishes one sound from another having the same loudness and pitch. It distinguishes one sound from another that had the same loudness and pitch. Both the sounds have different sound effects. For example, when the frequency and the amplitude are the same, we can see that one sound waveform for a guitar is different in wave shape than the sound wave from a sitar. Despite having equal loudness and equal pitch, we still notice a difference in quality or timbre due to the actual shape of that wave. Next, we're going to look at standing waves and harmonics. Standing waves are those where the waves appear to stand still at nodes as they propagate back and forth. Nodes are going to be the areas where the amplitude is always 0. Antinodes are areas of maximum alternating amplitude. Let's look at one example for the harmonic frequencies of a tube with one closed end and the other being open. The first frequency is always called the fundamental frequency, or F sub 1. The F sub 1 harmonic, or the first harmonic. In this particular case, with a singly sided closed tube, the fundamental frequency will have one single node and one antinode. The node being as this wave travels and then travels back out. The node is where there's going to be no change in amplitude from up and down. It will constantly stay still, or it looks like it does at that point. And then the antinode is where we have our maximum displacement of amplitude. For the next harmonic frequency, we're going to have the third harmonic frequency, which essentially has one full oscillation, or 1/2 an oscillation, 2/2 of an oscillation, 3/2 of an oscillation. Now then, that would have two nodes, or 2 points, where there's no change in amplitude, and then 2 points of antinodes. And then the fifth fundamental frequency in this case is going to have 3 nodes, 1, 2, 3, and 3 antinodes. And what we're looking at is 1/2, 2/2, 3/2, 4/2, 5/2, or 5 half wavelengths. Now, the length of a wave, or the length of distance a wave travels through some structure, is correlated to its wavelength in this sense. Length we're going to treat as this long side of each tube. For the fundamental frequency, the length of our tube will equal 1/4 of our wavelength. That's more relevant for trying to determine the wavelength. For our third harmonic, the length side of our tube is going to be 3/4 of our wavelength. And for the fifth harmonic, it's going to be length equals 5/4 of our wavelength. Therefore, essentially, our harmonic frequency, S sub n, whether the first, third, fifth, seventh, whatever, F sub n is going to equal the velocity of that wave divided by its wavelength. The frequency length velocity equation, if we replace everything, fundamental frequencies or harmonic frequencies are equal to n divided by 4 times V over L. And we go one step further. L, the length, is going to equal N over 4 times the wavelength. N just being what harmonic are we talking about? The first, second, or first, third, or fifth? Something we should know is when it comes to a tube with one open end and one closed end, we cannot have even harmonics. We only have odd number harmonics, the first, third, fifth, seventh, ninth, 11th, and so on. This situation with a single closed end and an open end is approximately modeling the ear canal or the human ear, from the outside ear to the eardrum. For an ear canal of approximately 25 millimeters in length, determine the fundamental and third harmonic frequencies for a sound wave traveling 346 meters per second. Also determine their respective wavelengths. Well, our frequency is just N over 4 times V over L. So our first harmonic or our fundamental frequency for the ear canal is going to be replacing this N with 1 quarter times 346 meters per second over 0.025 meters. The 25 millimeters converted to meters. This will equal 3,460 inverse seconds, or 3,460 hertz. We could also say that equals 3.46 kilohertz. The third harmonic frequency, we're going to replace N with a 3. So 3 quarters times 346 meters per second over 0.025 meters. That is going to equal 3 times the fundamental frequency, which is simply just this ratio times 1 quarter. So 3 times the fundamental frequency, or 10,380 hertz, or 10.38 kilohertz. So going forward, once we know the fundamental frequency for a tube with a single closed end and open end, every next harmonic would just be some multiple N times the fundamental frequency. So the fifth one would be this number, 340 hertz times 5. For the seventh harmonic, it would be this number times 7, and so on. As far as getting the wavelength, well, rearranging on one equation, we have wavelength of some harmonic n equaling 4 over n times the length of our tube, or wavelength is just the speed of sound divided by its frequency. Well, if we solve for y1 as 4 over 1 times 25 centimeters, that equals 100 centimeters, or 100 millimeters, which is the same as 0.1 meters. Wavelength equals velocity divided by frequency. Well, that's going to end up getting us 346 meters per second divided by 3460 hertz, or again 0.1 meters. For the third one, we have 4/3 times 25 millimeters, or 2/3, which is 33, or 1/3 times 33.3% meters per millimeters, and or 0.033 repeats meters. Now let's look at the harmonic frequencies of an open-end column. So a column, a tube that is open on both ends. What we're going to see is for the first harmonic, we have one half wave, and then we have another half wave. For the first harmonic, or the fundamental frequency of this system, the number of nodes will be 1, and the number of antinodes will be 2. For the second fundamental frequency, we have 1, 2, 3, 4. We have 4 halves. We have 2 nodes, 1 and 2, and 3 areas of maximum change in amplitude. And then for the third harmonic, well, we're going to end up having 3 nodes, 1, 2, 3, and 3 antinodes. 1, 2, 3, 4. And I should say 4 antinodes. For the most part, the equations are the same. Harmonic frequency is just the speed of that wave divided by its wavelength. Frequency length velocity equation is the frequency of that harmonic is going to equal n divided by 2 times wavelength, or times frequency divided by L. And L in this case is going to be n over 2 lambda, n over 2 of the wavelength. And we're talking about the first harmonic, then replace n with 1. We're talking about the second, replace n with 2. For open-end columns, it is possible to get even harmonics. So we have 1, 2, 3, 4, 5, and so on. We can do some of the same math that we already did before, but instead let's go forward and look at a closed-end column, which is what happens in an air column or strings. The first harmonic frequency, that's just going to be L, or 1 half, and then another half. The second harmonic is going to be 1, 2. The nodes in the first harmonic are going to be 2. The antinodes are 1. For the second harmonic, the nodes are 3 and the antinodes are 2. For the fourth harmonic, the nodes are 4 and the antinodes are 3. Collaborating these two, it is the length is equal to 1 half of the wavelength. Bring this forward, our frequency length velocity is going to be the same. It will be frequency equals n over 2 times nu over L. And L is just n over 2 times wavelength. The biological anatomy of hearing. We have the outer ear, the middle ear, and the inner ear, and some various other components from there. The external or outer ear consists of the pinna or auricle, the outside part of an ear. The external auditory canal tube connects the outer and middle ears. Typical membrane eardrum divides the external ear from the middle ear. The middle ear, or the tympanic cavity. Ossicles are the 3 connected bones in which send sound waves. To make it easier, they are the sound waves, let's see, they are the malleus, incus, stapes, they're eustachian tubes, a canal linking the middle ear to the back of the nose, needed to equilibrize pressure in the middle ear and prevent hearing loss. The inner ear consists of the cochlea, a location of nerves for hearing. It also includes the vestibule, which is a location of receptors used for balance, and the semicircular canals, which have resistors for balance as well. Sound waves, vibrations through the external auditory canal and vibrate the eardrum. These vibrations are passed down the ossicle bones, which amplify the sound upon the way to the inner ear. Upon entering the fluid-filled cochlea, sound waves are converted to electrical signals, which can then travel through the auditory and nerve onto this onto the Okay. Well, we just finished hearing and sound. Now let's get into vision and lights. We have the electromagnetic waves as well, not just sound waves for interpreting senses. Electromagnetic waves include radiation along the entire electromagnetic spectrum. Radio waves, infrared waves, microwaves, visible light, ultraviolet light, X-rays, and gamma rays. They exist as non-mechanical transverse waves. Furthermore, electromagnetic waves consists of an electric wave component and a magnetic wave component, and their speed is constant. The speed of light, also the speed of gravitational waves, is roughly 3 times 10 to the 8th meters per second. So just a showing, here we have different examples of light across the electromagnetic spectrum. One thing to note is the wavelength is longer or larger for the end that has lower energy. So radio waves, microwaves, they can be on the orders of kilometers of distance between those two crests. As we get between 380 nanometers and 760 nanometers, blue light and red light respectively, that would be the visible light spectrum, which includes the narrow range of all the colors we're able to actually visualize. And then toward the higher frequency, higher energy end, or the lower wavelength end, we have gamma rays. Each of these waves have a different particular use. Radio waves are good for broadcasting radio and television. Microwaves are good for cooking, radar, telephone, and original signals. Infrared is great at transferring heat, whether from the sun, fires, or radiators. Visible light makes things able to be seen. Ultraviolet light is absorbed by the skin and used in fluorescent tubes or used to activate, say, inactive vitamin D, which then becomes active in sunlight. There's also X-rays, which are used to view inside the bodies and objects, and then gamma rays, which are used in medicine for killing cancer cells. Reflection and refraction of light. Reflection, as dictated by the law of reflection, the angle of reflection equals the angle of incidence. Now then, the ray reflected travels in the plane of its incidence. Refraction is when light passes from one medium into another. The beam changes direction at the boundary between the two media. The property for the medium is called index of refraction. Eta is simply equal to the capacitance divided by the speed of light, or my apologies. Viscosity is simply going to be oh dear, here we go, N not eta. N is going to be the refractive index, and that's equal to the speed of light in vacuum divided by the speed of, or the velocity, the frequency of light, the speed of the velocity of light in the respective medium. As light travels through different mediums, its speed gets altered just a little. So refractive index is just the speed of light divided by the speed of the light in the particular medium it's in. Some other things we have is Snell's law, or the law of refraction, which simply states that sine of angle 1 times sine of the angle of incidence divided by sine of the final angle is equal to the refractive index of the second tribe divided by the refractive index of the first. Or we could just use V1 over V2. Theta 1 and theta 2 are the angle of incidence in medium 1 and the angle of refraction into medium 2. To calculate this stuff, essentially we have is light refraction, which bends away from the original axis. That's essentially where the medium that we're currently in has a lower refractive index than the medium light is about to enter or refract into. In the opposite case, where the initial refractive index is less than the refractive index of our second medium, then light refraction bends toward the normal axis. Where N1 is greater than N2, light refraction tends to bend away from the normal axis. Now, let's just talk about that. Let's say we have some light wave, some ray of light that bounces here and reflects. The reflection is going to be our angle of incidence. Its reflection is going to be the angle of reflection. Now, let's say instead, for every time that a certain amount of this light reflects, there will be a certain portion that refracts instead. As we have something refract, we have some new theta restraint, and now what we have on the right side is something similar. But in the first case, we have light that's traveling at a medium of 1, plane air, into a medium of 1.45. And in this example, light is at 1.45, and he's trying to get it down to 1. Let's see. Something to note is that if we ever have reflection, then it will reflect at the same angle as the incidence angle, and that's with respect to the normal axis, this being the normal axis. And then we also have an angle of refraction. So let's start looking at this. For a ray of light approaching an interface between air and kerosene at an angle of 0 or at an angle of incidence of 26 degrees, determine the angle if it were to reflect. Determine the angle if the ray were to relax instead. Well, theta I is just going to be 26 degrees, or whatever that fraction you get. Pi equals something over something, or something like that. Here what we have is big sin, which is N2 theta 2 plus N1 similarly 1. Now, based off of Snell's law, the refractive index of one layer times the sine of its incidence angle is going to be equivalent to the refractive index of the second layer times sine of its angle, which let's fill in what we know. We don't know theta 2, but we know that theta 1 is 3 times 2yl. Now, sin of theta is going to equal n1 theta sine theta 1 over n. When we start changing the value to 26 degrees, we get 1 minus sine of 26, which arctan of that function, or tan inverse, would be sine of 26 degrees raised to 145 divided by 145. Going further in this problem is just to show the basics of what we did, which was, which was as, okay. Now, if we ever have a situation where we have light traveling through a higher refractive index than the next layer, we're going to have what's called, a barrier. The critical angle is when a barrier to refraction, any ray of light entering with an incidence angle greater than angle C across the capacitor, refraction will not occur and only reflection will. This is only calculated if N1 is greater than N2. Think about it this way. We come in at some angle, and we don't want to look at which ones reflect. We want to look at which ones refract. First thing we do is write Snell's law. N1 sine 1 equals N2 sine of theta 2. Rearranging some stuff. What we want to find out is what's the maximum angle we can have for angle of incidence that this would actually be traveling at a right angle, and therefore this equation would not be necessary. Rearranging some things, we eventually get sine of our critical angle equaling N2 over N1. The reason why sine of 90 degrees dropped out is because that is just equivalent to 1. And then we're left with sine of OC equals N2 over N1. The critical angle is just the inverse of that value, or arc sine of 1.45 over 1. That encourages me that you have 43.6 degrees. What this says, any ray approaching the interface of more than 43.6 degrees will never refract into the next medium. It's just too narrow for something to be released and then travel through the air. Next thing we have is the lens maker law, which says that 1 over the frequency is just N2 over N1 minus 1 plus 1 over R1 plus 1 over R2, the radii. I'll let you all read that. C1 and C2 are the centers of curvature for the front and back surfaces. Here what we have is some centers of curvature, C2 and C1, approaching some eyeglass. These are the points where all of these points are branching off from or collapsing into. These are known as, complex systems. Let's look at just a single concave situation or convex situation. Here we have these two that come together into F. And then we have our new setup, which also consists of two boiling points, and the proper wavelength is going to be situated up here. Now, using the lens maker law, a lens material n equals 1.2 has convex centers of curvature, each being around 10 millimeters. Determining the focus length for light in air is around 1 over the wavelength of n2 over n1 minus 1 plus r1 over r plus r2. And then that's going to equal 1.5 divided by 1 meters times, times Belafonte. Therefore, our frequency will be 0.04 inverse meters or over meters. Now let's look at the visible light spectrum. Here we have a nice equation. We already related speed and velocity and frequency. Now let's look at energy, which is just Planck's constant h times our free circuit diagram. E is the energy in joules usually, F is the frequency of light in hertz, wavelength is the distance between those points in meters, a Planck contest is 6.626 times 10 to the negative 34th moles per second, and then the speed of light, c, which is also the speed of gravity, is 3 times 10 to the 8th meters per second. Now let's look at the biophysical anatomy for vision with the eyes. Initially, in the cornea, which is clear and dome-shaped surface where all interpreted light enters, the pupil light then passes through the pupil. The amount of light is regulated by the iris, or colored portion of the surrounding pupil. Light then is footballed by the lens and travels through the vitreous humor, jelly-like material that fills the eye. The light is focused by the lens towards the retina. The retina is the back layer of the eye, which is lined with light-sensitive nerve cells. The image that reaches the eye is reversed from what is true. The optic nerve then carries electrical signals produced in the retina and sends them both to the brain in order of the usual cortex. Those electrical signals are converted into images, like for wisdom. Along the retina, the back of the eye, there are going to be cone cells and rod cells. These things right here. The primary cells for vision are rod cells and cone cells. Rod cells in vision during their lifetime while cones help with color, vision, and detail. As light reaches those cells, a series of biochemical reactions occur, wherein the electrical impulses are produced and sent to the optic nerve. The light of the retina in the materials of lutea, yellow spot, this carrier of the masculine lutea is the furthest complaints, which contain only one cell and is used for seeking fine line detail clearly. Now let's look at photoreceptor concentration. Rod intensity reaches a maximum around the perimeter of the yellow spot, that is the 20-degree mark away if we're looking from our eyes straight down. Cones decrease sharply in density as we move further away from the yellow spot. The nerve fibers would receive information, which perceive, but they're like protozoan photoreceptor cells. Converse in the blind spot, wherein there are no photographers. Temporal means towards the temple, and nasal means toward the nose. The outer segments of a rod cell contains the photosensitive chemical rhodopsin. Visual purple is another name. Approximately 100 million rods line the retina. Rhodopsin is a complex protein called scotopsin and 11-cis-retinol. The latter is derived from vitamin A. Rhodopsin decomposes when exposed to light, which changes 11-cis-retinol to all-trans-retinol. Rhodopsin then breaks down into various intermediate molecules and finally metarhodopsin. The second, activated rhodopsin. In early second, metarhodopsin 2 is activated in under a second. This chemical causes electrical impulses which are then transmitted to the brain. On the right side, we have the example of a nucleus with an outer segment of a rod containing photosensitive chemicals. And here's just the complex body biochemistry of rhodopsin, where in the presence of light, it breaks down into one molecule, which part of that can turn into scotopsin, or if it gets used further down, part of it can be turned into 2-cis-retinol, and then the combination becomes rhodopsin again. Now we're going to look at cone cell response. The outer segment of a cone cell contains one of the 3 photochemical cone pigments. Going a little bit further back, just to show that rods, they have a lot of density up until the yellow spot, and cones have a lot of density in the center of the yellow spot. And at around the 20-degree mark, this is known as the blind spot. Sticking with cones, though, the outer segment of a cone contains one of 3 possible photochemical pigments. Approximately 7 million rods line the retinal, or approximately 1.7 million cones line the retinal. Cone pigments are similar to those in rods, however, the scotopsin portion is replaced with photopsins, making them color-sensitive pigments made of retinal and photopsins. What we're looking at here is the core pigment in a cone cell will be one of the following. If we look at a registered agreement, and then next is long wavelength, and the L-type transverse waves are closed. Now it'd be red sensitive pigment. If we're looking at medium wavelength or M cones, that will be green sensitive pigment, and then blue sensitive pigment is short wavelength S-types and their criticisms. Here we're looking at the 3 types of sensitivity of cones. We have L cones for long wavelength. We have green sensitive or N cones for medium wavelength, and we have blue sensitive or S cones for small wavelength. In any case, what we have here is if we have all of the cones in our eyes, we have an easy time distinguishing between this set of colors and this set of colors and this one right here. Getting into color vision, we can have photopic vision, which is normal daylight vision where there is enough illumination for cones to be active and hue to be perceived. Scotopic vision, which is the ability to see in reduced illumination, such as during moonlight, and Purkinje effect is the tendency of the peak sensitivity of the human eye to shift towards the blues end of the visible light spectrum during low financial lows or levels. These types of color blindness make it difficult to tell red and green colors apart. This would be red-green color blindness, of which there are 4 types. There's protanomaly, which marks red that looks more green and less bright due to misfunctioning red cone cells. Deuteranomaly has to do with which makes green light look more red due to misfunctioning of the green sensing cone cells, of which there's green, red, and blue. Protanopia is the inability to distinguish between red and green during a missing test. So it may behoove you to study. Then there's deuteranopia, which is the inability to distinguish red and green due to missing green cones. In case it wasn't said, L stands for long wavelength, medium stands for medium wavelength, and S stands for short wavelength. As far as the last one, deuteranopia, that is the inability to distinguish red and green due to missing green sounds. Now that was red-green color blindness. There's also blue-yellow color blindness. These types of color blindness make it difficult to tell blue and green apart, as well as yellow from red. There's tritanomaly, which makes it difficult to distinguish blue and green colors in yellow and red due to misfunctioning blue cone cells. Tritanopia, unless distinguish between blue-green, purple-red, and yellow-pink will all get confused. Also makes cookies look more delicious. Near complete and complete color blindness, there's monochromacy, and then there's achromatoplasia, which has to do with a range of minimal to be color sensing capabilities. And then there's, blue line, and then that's. And that would appear to be it. In any case, that covers vision and whatnot. And just around the 53-minute mark. Thank you all for coming to this lecture series. As always, likes and subscribes are not necessary, but they are fun to see. In any ways, peace.